Hey everyone. So today we're going to be working through the week 4 questions, which you can find on iLearn in the course materials page. Um, and we're just going to go ahead and get started. Hope everyone's doing well. If you have questions, remember to leave them in the comments. Uh, Other than that, let's go ahead. So for number 1, what we have, let me pull it back up on this one, is a battery with some voltage hooked up to a capacitor with spacing D. And originally, this battery has some delta V, just some standard delta V bat. And what we want to know is what happens if we replace that battery with another one that has delta V bat times 2. So just double the voltage difference of the original battery. So for part A, it says, does the potential difference change over our capacitor? And just thinking conceptually, the reason that there was a voltage difference over this capacitor initially was because of the voltage from the battery. So we can say, right, like initially delta VC was just equal to delta V battery. Now, after, it has to be equal to whatever, again, the delta V of our battery is, which is now 2 delta V bat. So in this case, the voltage over the capacitor is going to double as well. And that's just because it comes straight from the battery, right? And now we want to know, does capacitance change for this capacitor? And this one can get a little tricky depending on how you look at equations. But the thing to know conceptually, and if you want to look it up specifically, it should be in page 725 of your book where it starts talking about capacitors. For capacitors, the value of capacitance is solely based on geometric properties. So the area of the capacitors and the distance of the spacing. That's if we're strictly looking for capacitance. So initially, we have this equation, C is equal to epsilon naught A over D. Since we haven't changed the area and we haven't changed the spacing, nothing is going to change after the fact. So C is still going to be equal to epsilon naught A over D. And that's because capacitance is strictly geometrical. And then for C, what we're asking is, does the charge change, right? So we want to use the other equation where we have initially that the charge was equal to, and I'm referencing my notes over here because I forgot it off the top of my head, the voltage difference. So in this case, it's delta V bat times capacitance. After we change it, right, so now our delta V battery, the delta V that we're using is double. So Q is now 2 delta V battery times C. And that's kind of where that counterbalancing comes from. So now our charge has doubled, right? So these are going to be the answers for number 1. We're going to go ahead and move on to number 2. All right, so here we have question number 2. I've drawn it out. And what we want to know is, what is the equivalent capacitance of this circuit? So if we combined all these capacitors into a single one, what would be the value? So the easiest thing to do is to combine this 20 and this 10 first. If we have capacitors in parallel, then the equivalent capacitance for just these two is the sum, right? So we can take 20 plus 10, and that's just going to give us 30. So we can redraw this circuit. And I'm just going to kind of draw it a little bit quicker here. Like this. So this one is still going to be 10, and now this one is 30 microfarads. And now to get the total equivalent capacitance, we just need to combine these two. And the way that we combine capacitors in series is by adding the inverse. So our total equivalent capacitance is going to be 1 over 10. So this 10 microfarad capacitor up here plus 1 over 30. And then we're going to take the inverse of that. So what this is going to end up giving us is 4 over 30 to the inverse. And if we just plug this into a calculator, or however you want to do it, you're going to get 7.5 microfarads. So the thing to remember for this problem, capacitors in parallel add normally, and then capacitors in series add inversely, right? So we add the inverse of them. So yeah, and then let's go ahead and move on to number 3. So for number 3, what we're being asked to do is, or well, first what we're told is we have a single 75 millifarad capacitor, right? And what we actually want is a 50 millifarad. So we need to figure out a way to make some combination of capacitors to get 50 millifarads, right? And it says, should we join them in parallel or in series? So if you remember what we said before, when we add capacitors in parallel, right, we're just adding them normally. So there's nothing we could add to 75 to get 50 other than negative numbers, but you can't have a negative capacitance. That just doesn't make sense. So we know that they have to be added in series, for one. And then we can just kind of use some equation. So we know we can kind of draw a circuit to make this a little bit more realistic. We know one of these is 75 millifarads, and we don't know what this one is, but we know that we want the equivalent capacitance to be equal to 50 overall for this circuit, right? So we can just kind of rearrange that other equation. We know that 1 over C equivalent is equal to 1 over C plus 1 over 75 in this case. And then we just kind of rearrange how we want it to be. So now 1 over C is equal to 1 over 50. I'm just plugging in the 50 for C equivalent. And then we subtracted the 175 over. And then we need to continue to combine these two. So we're going to have 1 over C. This will become 1 over 150. And then if we just take the inverse of both sides, we're going to get that the capacitor we would need to combine it with is 150 millifarads. So again, this is like in the future, if you're an electrical engineer, right, you need a very specific kind of capacitor, but you don't have it. If you can combine some other ones, you can get the value you need. That's essentially kind of what this problem is trying to employ. But yeah, these problems get kind of tedious, but if you're still stuck on like how to add things in parallel versus series, it just comes down to practice. So hopefully this was helpful, and if you're still struggling, just got to keep on practicing. Leave questions in the comments and we'll get around to answering them when we can. Other than that, good luck studying and hope to see you all in session.